Hello Hambini fans and welcome. In today's episode we're going to be talking about Zipp wheels and the dimples that are on them. Now, following on from my Aerodynamics masterclass video, I had a lot of questions, and one person in particular, a chap called Barry from Oklahoma in the USA, he emailed in and asked if I could explain how their dimples work or don't work. So that's what this is going to be about. Now, for the unfortunate person that I am, I actually have a set of these Zipp wheels on my bike. So these Zipp wheels are 808 and they have these dimples on them. If you're wondering why they're on my bike, even though I'm about to tell you they're a bag of wank, it's because they were cheap. And price is a thing that is very, very important in the world of bicycling. So what I've tried to do here is I've zoomed in on the wheel, and what you can see is here is the tyre. So it's a Continental GP4000. The tyre hooks into the bead, then we've got the rim brake track here, and then straight after that we have this area of dimples, and these dimples are supposed to be a bit like a golf ball. And the way they're supposed to work is you generate what's known as a turbulent boundary layer, and a turbulent boundary layer sticks better to the wheel, thereby reducing drag. So as far as the rim mechanics goes, there's really not much to it. It just looks like any other wheel apart from these dimples. To explain what happens on a technical basis, I really need to show you some technical slides, so we'll do that now. What I've done is I have done some slides to illustrate why Zipp wheels aren't so good. And I've named this presentation of PowerPoint which is Zipp wheel dimples and why they are shite. Now, some of my critics say I'm a child, immature and all of this stuff, so I've written on the side of my presentation, by Hambini, aged 5, in my best paint handwriting. Right, let's carry on. Right, first of all, in order to understand what's going on with these dimples, you have to have a very basic understanding of fluid mechanics. So I'm going to go through that now. First thing is Reynolds number. So Reynolds number is a dimensionless number. It has no units. It's a bit like percent. So if you say, what is 5% of 100? 5. The 5% does not have a unit. So the percent doesn't have a unit, or per 100, but it's not a unit. A Reynolds number is rho VD over mu, and it basically defines whether the flow will be laminar or turbulent. So to go through this, if I turn the laser pointer on, pointer options, laser pointer, the rho is density. For water it's 998, for air it is 1.225. That can vary depending on whereabouts in the world you are. V is velocity, and that is measured in meters per second, not in kilometers per hour. D is a characteristic dimension, and mu is viscosity, and I can never remember whether it's kinematic or dynamic, but it's related to the one of them is 1 divided by the other. So viscosity divided by density gives you kinematic or dynamic. I can never remember it, but it's not that important. And to be honest, I don't give a shit. Right, and I'll give you a number. And the number defines, as I said previously, whether it's laminar or turbulent. The next thing we have to go through is another thing that you've probably heard of called drag coefficient. Now, drag coefficient is another dimensionless number. So it has no units, it's not measured in meters, kilograms, seconds, what have you not, doesn't have any of that. And the formula for drag coefficient is CD, which is your arbitrary number, is the total drag force divided by half rho V squared A. And to go through these, CD is just the drag coefficient, D is measured in newtons, half rho V squared, so the whole of that term is dynamic pressure. So the rho is density, again for air it's 1.225, V is measured in meters per second, and A, which is the frontal area of the object. I mean, some people call this wetted area, and there's always a huge debate about whether it's wetted or frontal or exposed to air and all this kind of stuff. I'll leave that to the scientists. It is used to determine how aerodynamic an object is. And if you were to define it in words, it is basically the amount of drag per unit of area. So you could say it is the equivalent of, what could you say? Well, yeah, it's just the drag per unit of area. Now I've got some more practical examples. So the drag coefficient of some popular shapes. So we have a bowling ball or the sphere, drag coefficient 0.47. A half a sphere 0.42. Now you'd probably expect this to be less aerodynamic than the sphere, but it's not, and it's to do with this vacuum that happens around it. Triangle or cone, cube, and then when you get down to streamline body, so a streamline body is 0.04, so it's 10%. Or not, around 90% reduction, or 10% of the absolute value, and then a half streamline body, and then I've got some other like select drag coefficients for you. So if you want to hurl a brick at someone, bricks have a drag coefficient of 2. Next one, and this is more appropriate. Rider on the hoods, CD 1.1. Rider on drops, CD 0.85. TT position, CD 0.7. So you can see there's quite a big reduction between riding on the hood and going to a TT. It's like 30% for 30%, depending on which way you're going. 30%, and then another there. That's not 15%, there's a bit more. Oh, I can't do the maths. Anyway, right, let's move on. Right, I'm going to give you a practical example now. All of these people come out with presentations, and if you go reading on the forums, they're all obsessed by freaking numbers, and they don't give you a practical example. So I'm going to give you a practical example, which is this car. So this is a Opel or Vauxhall Calibra. When it came out, it was the most aerodynamic car on the planet, and it's got a drag coefficient, or had a drag coefficient because they don't make it anymore, of 0.26. That is pretty good. Most cars of this era, so of where we are now, 0.3 is kind of the benchmark. So 0.26 is really quite good. The next one is an Audi A2, and the drag coefficient of that is 0.25. So when I was much younger, this was like the favoured car of rich graduates. So graduates who had typically ejected themselves from Bristol University used to come along and drive around in these things, which I at the time couldn't afford, but never mind. But I mean, well, they were a lot younger than me anyway. But we digress. I hate digressing. The drag coefficient of that is better than the Opel, even though its box looks like a box or two boxes. And the main, well, I wouldn't say the main, but some subtle design features that contribute to the improved drag coefficient are these fairings. So the ones around the wheels, they manage the the airflow around the wheels much better. And that's partly to do with the way that manufacturing allowed them to make those pieces. So on the old Vauxhall or Opel, that was part of the front wing. And there was also part of the, I don't know, what do you call that? The rear B to C pillar kind of panel. Whereas on the Audi, they were actually plastic stuck on. So they were able to do that, whereas they weren't able to do that before. Also on the roofline has quite a big slope, or curving slope on it, and that aids to reduce the drag coefficient. And then the bumper didn't have it was like a smooth structure. On this side of the car, the ability to reduce drag is not really that important, because you've got high pressure air coming in, or ram pressure increase, so the air will stick whatever. It's when you get towards the back of the car and you're trying to stop the air from detaching suddenly that you get these issues. Right, next one. Yeah, I've said that. Next one. Oh yeah, I don't know what happened here, but I've managed to spell Boeing wrong. And then when I went on the internet to find a picture of a Boeing Boeing 747. The only one I could find was this one of this Qantas B747, where this mindless vandal had drawn some terrible graffiti on the side of it, and I don't know who would do such a thing and then post it on the internet. The drag coefficient of a 747 is 0.03, there or thereabouts, and it's largely dependent on which configuration it's in. So you could say, is it in takeoff mode, in which case the drag coefficient is a lot higher. Landing mode, drag coefficient even higher still. And then which particular type of 747. So there are many variants. Some are slightly longer than others, and the clue to telling which one is which is almost to look at the wingtips. They're quite a design feature of aircraft of a particular brand. Right, so we've digressed a little bit, but I wanted to give you the practical examples. What you have to understand is drag coefficient varies with Reynolds number. So if you have a drag coefficient of a bloke in a wind tunnel, matey boy in a wind tunnel, and then which is based on air, and then put him into a wind tunnel that is based in water, so take the air away and put him in water, his drag coefficient will actually change. So it's not fixed, irrespective of all these other parameters. So, and that's what this statement says. Drag coefficient is a function of speed, viscosity, and I've used water and syrup, water versus syrup, and shape. But it's a function of all of them. So if you change one of them, your drag coefficient will change. So for example, another one, if you are at sea level and then you measure your drag coefficient, if you go up to Mexico City, where the air is thinner, the air is less dense, your drag coefficient will change. That's probably not that widely known, but I'm telling you, that's life. And also the viscosity of air, so how runny or thick it is, that will also change. If you're staying, if you're in the same fluid, so if you're in air and the object shape stays the same, then you can turn that equation into a drag coefficient is related to speed. So the faster you go, generally speaking, your drag coefficient will get less. And that's because you're not shedding as many vortices and a few other bits and pieces. It doesn't apply to all shapes, but this graph gives you an indication. So if you took the flat plate, doesn't matter really what Reynolds number you're at, it's pretty constant drag coefficient. The circle or the ball, this is a bit of a peculiar one, because as you go along, it suddenly drops and then it starts to pick up back up again. And then the aerofoil, this is, as the speed increases, you are reducing your drag coefficient, and then you have a big reduction, and then it sort of peters out and stays pretty much the same. And then what's the other one? Ellipse. So that's, if you took a frame, if you took a round tube and then inclined it at an angle, which is what you've basically got on a down tube, it looks more like an ellipse, so it would follow this sort of profile. I mean, modern bikes tend to have more of an aerofoil profile, but there's your difference. Right, I've picked the ball for this one because the original, well, there's a lot of data about basically golf balls. And a golf ball is a sphere, so I went and lifted this slide from some fuckers called NASA, and it shows two lines, a line for a smooth ball and a line for a rough ball, and the drag coefficient that varies with Reynolds number. So basically you're getting faster as you go towards the right, to put it bluntly. That's what's happening, you're getting faster. You could say, the other thing you could say is the air is getting more dense. But anyway, right, so yeah, let me get that. Right, this region here is called the Laminar Region. So air that's flowing over the ball is laminar. So it'd be like the utopian airflow. So you've got a laminar boundary layer. You've got lines that are coming in, very nice and smooth. You know, it's perfect, just textbook. This bit over here is turbulent, where all hell breaks loose, and it's very difficult to model unless your name is Hambini. But joking aside, in that region over there, it is a lot more difficult to model airflow, and you're at a higher risk of getting it wrong. In here, this is the transition zone. So you're transitioning from, you know, this smooth, perfect airflow to turbulent, all over the place, slightly chaotic flow. The golf ball happens to operate in this region here. Okay, so the golf ball is around Reynolds number 10,000. And what's happening is the golf ball, by putting dimples onto the golf ball, you are going from this position to this position. So you're moving downwards. So you've got the smooth ball, add the dimples, you go down here. So it has a big difference on drag coefficient. So your drag coefficient is 0.3 lower by having the dimples. So it's, what's that, 0.5 to 0.2? That's 60%. I can't do maths. I'm terrible at maths. I'm just terrible at maths. Right. So the drag reduction is made up of drag is made up of two components. So there is skin friction, which is just air coming over your skin and it's rubbing it. And by rubbing it, it causes friction. If you were to go and get some really, really fast moving air, you would feel heat on your skin because the friction is so hot. Space shuttles, as they are coming through the Earth's atmosphere, the air is heating the nose cone up so much that that's a special material, a black material on the front of a space shuttle. And the other component is pressure drag. Now, pressure drag is the wake that is sitting behind you. So if you imagine my huge head, if I'm moving along, well, okay, let's presume I'm static. So if I'm not moving at all, there is no pressure wake behind me because, you know, all the air is static. But if I move my head forward, then I'm pushing air in front of me, which in turn billows over my head and fills the space behind it, and that is the pressure drag. So when you put dimples on the golf ball, it increases the skin friction drag and generates a turbulent boundary layer. The pressure drag reduction is more than the increase in skin friction drag, so you get a net drag reduction. Right, so this is a visualization. So up here we've got the laminar boundary layer, well, they're both laminar, but the undimpled golf ball, and down here we've got the dimpled golf ball. What happens is when you go from here, which is the smooth surface, to the turbulent or the dimpled surface, the separation point moves further along. So it moves to sort of the 2 o'clock position, as before it was sort of between 11 and 12 o'clock. This bit here is your increase in skin friction drag, so the difference between 11 and 2. But the reduction in pressure drag is the reduction between sort of 12 o'clock and 2 o'clock. This to this, so the reduction in the wake is what gives you the reduction in drag. And I've just put there a turbulent boundary layer delays separation, so air sticks better, and you'll see this on things like trainer aircraft or aerobatic aircraft. So those people watching in the UK, the Red Arrows, or I think in the US is it called the Blue Angels, those aircraft have what are known as Vortex Generators, which is pretty much the same thing. So you're generating turbulent boundary layer. It allows them to, you know, do some ridiculous maneuvers and not have the wings stall. Right, So this is the Zipp Firecrest profile, which I lifted from some of their literature, and this is one that I drew in a CAD program. So it's just mainly so it's easy for me to annotate. So, but it gives you an idea of what's going on. So this is the tube, this is the tyre, this is the sort of rim, this is the bead where the tyre hooks in, this is a really crap spoke hole, and this other grey area is part of the section of the wheel. On a Firecrest wheel, this area here is what's supposed to be dimpled, and that's where the rough surface is. What's supposed to happen is, I've just made that go grey, but you've got these streamlines which come over and they wrap around the tyre and wheel rim and then generate a very, very small wake, and ideally no wake as it goes round. It reduces the wake by delaying separation. That's what the dimples are supposed to do. And they're also supposed to keep the flow attached for longer when the wheel is at an angle. That statement, keep the flow attached when it's at an angle, is straight out of Aerospace 101, because as I mentioned earlier, the red arrows and blue angels, when they are performing their acrobatic maneuvers, they are pushing the envelope of the ability for that aircraft not to stall. Right, so now we've got the Zipp dimpled versus the Zipp non-dimpled, and the difference in airflow. So you've got, that is your Zipp dimpled and that is your non-dimpled. There is no difference with dimples in steady state or in transient analysis. Try it either way, there is no difference. The dimple size is mismatched for a bicycle wheel. I want to add a bit further onto that. The dimple size and the location aren't right for a bicycle wheel. So what's going wrong? So here is the Firecrest profile and the dimpled area again. Ideally, you need the turbulent area to be over here, which is getting on towards the high pressure side. So where it goes from being laminar to turbulent, you need to be basically on the tyre, on the edge of the tyre. That's ideally. The next best place to go turbulent is here, so around the bead, where the bead of the tyre goes in. There's a bit more risk in that because there's more opportunity to get wrong. Yeah, I've just said that. And this is it. I mean, this has been designed by an amateur, and a shite one at that. I don't know if they played freaking golf or what, but it's just diabolical, crap, rubbish. Now, my critics usually have a go at me for being fairly decisive, opinionated, and what's the other word? Bit of a wanker, really. But parking that to one side, you know, my statement is: have they been parachuted in from the marketing department? Because I don't know what kind of aerodynamicist would actually put those dimples where they've put them. They must be a complete fruitcake. And if I was in charge, I would clearly sack them, because I can't tolerate imbeciles like that. And remember what Pete, my mentor, said: assume they are a fucking imbecile until proven otherwise. In this case, they are a fucking imbecile, and they've proven they are a fucking imbecile, so they should be sacked. Right, I've put this slide on because there's actually two different design philosophies with how you sort of get around this problem. The best one is the Mavic CXR type with the rim strip. So these yellow things here, you see that one there and that one there, they are rim strips which Mavic put on. The UCI banned them, but it's very effective across any speed range, whether in windy conditions, whatever. That is the go-to gold standard. So to bridge the gap between where the tyre seats and the start of the rim. The other way you can do it is the LIghtbicycle method. Now the LIghtbicycle WR56 is a bit of an oddball in the aerodynamics study that I did, because it's fairly wide, but it does quite well, and it would do even better if it was narrower. But this one is a bit of an oddball because it's got a trip ledge. So where the rim kind of sticks out past the tyre, I can't best describe it. There's a sort of bit that juts out. I don't know if, I'll talk about this a bit more. The size and the setback of the ledge. So the setback is the distance from here to here. It's well matched for the rim depth. So it's well matched for the 56 mil deep rim. So it's basically, it makes the air go turbulent here, and then it sticks, which makes it very effective given how wide the wheel is. But you've got a defined speed range. So if you're going really, really fast, you've actually got a slight reduction in drag. And when I say really, really fast, that's like 60 k's. If you can do that speed, you will be probably going downhill. That's when if you're chasing somebody, you'll need to pedal to catch up with them, because it's a bit ropey around there. And also, you're probably more likely to get speed wobble with this. I don't know if it's blind luck or judgment that's made that wheel the way it is, but as far as it goes, that one, the LIghtbicycle wheel and the Conti tyre together, 23mm tyre, are a very, very good combination. Now the guy that owns those wheels is the guy that does the control systems at the place where I work, or control surfaces. So he knows a thing or two about the movement of airflow around objects. But again, I'm giving him more credit than it's due, because he just bought them because they were cheap. So, so there we go. You know, a guy with PhD, all this, that, and the other, loads of letters past his name, and he bought them because they were cheap. But yeah, it's possible if you get the tyre completely incorrect, you could screw it up. And to get it completely incorrect, you'd have to be really, really screwing it up. I mean, if you put a Conti tyre on there or a Vittoria tyre on there, I don't think you'd make much difference. If you put something that was, because I think it's a 30mm wide wheel, if you put like a 28mm tyre on there, then the setback of the trip ledge may screw up. Just bear in mind, this diagram shows you a cut through the center line of the wheel, so level with where the quick release lever is. If you go up or down, we'll get a slightly different section. You'll get an elongated section. This trip ledge business is quite complicated compared to this. So the Mavic system, you've just basically flattened it. So if you've got rotation on it, it doesn't make any difference. Well, I was going to say it makes no difference. It makes, a small amount of difference. Whereas on this one, if you've got rotation, which the wheel inevitably will rotate, it's more complicated to get this dimension correct. And I don't know whether it's blind luck or judgment, but you know, that's just my opinion. And then the final one, which is, I've trademarked this, the cuntish shitbag scale of engineering fuckwittism. Right? We have the scale, which is this blue arrow here. On the right hand side, we have the lick, which means it's quite good. Then we have the shiz, which is not quite as good. Then we have not a shit bag, a borderline shit bag, definite shit bag, cuntish shit bag, and speck of shite on the anus of humanity. Now, to give you an indication of where the engineering of these Zipp wheels lies, I put in some select shit bags, or cuntish shit bags. So we have flow wheels, so they are definitely specks of shite on the anus of humanity. If you want to buy their wheels, then by all means do so, but just remember, you are not buying any engineering expertise from anyone who knows anything about aerodynamics. You are buying a set of wheels from a group of refrigeration engineers masquerading as, well, I don't know what they're masquerading as. Well, anyway, don't know. Right, Tifosi, they are a bunch of knobs, complete wankers. Yeah, we'll be coming to that in a different video. But yeah, Tifosi with the bicycle frames that are basically wank, tolerance wise. Cannondale, another bunch of shit bags. So they design a standard and then 40-50% of their bikes don't meet the standard that they designed. And then finally we have Zipp wheels, which are in the definite shit bag column. So the reason why I haven't given them a poorer rating is they're not really causing an issue in the sense that it's not probably going to drive you mad. It might drive you mad knowing that you're losing watts. That doesn't really drive me mad, but it might drive. It is not like Cannondale where your bike creaks, or Tifosi where the bike will shred bearings and you'll feel it. Yeah, it's a different kind of thing. So that's the Zipp wheel Dimples. Obviously Zipp wheel bearings, they are definitely cunty shit bags, but I haven't put that on this slide. And that's it. So that is this presentation. I really hope you enjoyed it. If you've got any comments, then use the comment box below. If you want, remember to hit the like button and subscribe. And if you've got any requests and stuff like that, then please type in the comments box. I do read all of your comments, but I can't respond to them all. It's just got to the stage where I'd spend basically a day replying to all the comments, but I do read them all and I do try and reply to the vast majority of them. But if you've got a specific query, then visit my website and then send me an email. Thanks very much, and until next time.